today's lesson, we are going to make or be looking at a summary of models. So we're going to be looking at the linear, quadratic, and exponential models. We're going to be looking at just a brief review of what the characteristics are of each, as well as then using all three to make or to determine which one is the best model for a given set of data. So if we look at the linear models, some of the characteristics, especially when we're looking at a table, is that the first differences are all the same. So if we look at what the y values are changing by, in this case, they're all increasing by 5. So that means it is linear. One thing to keep in mind, you want to make sure that the x values are also increasing by the same amount. Right? Equal changes over equal intervals. In our equation, y equals mx plus b, that's our general form for a linear model. M is our rate of change or slope. B is our initial value or our y-intercept. And then graphically, we have a straight line. For a quadratic model, when looking at a table of values, again, you check the first differences. In this case, going up by 10, 20, 30, 40. First differences aren't the same. It's not linear. So you check the second differences. In this case, they're going up by 10 each time. So that means it's quadratic. So quadratic, the rate of change is not constant, but the second differences are equal. So in this case, we're seeing that the second differences are equal. The x values are going up by a constant amount. So that means based off of this table, it's quadratic. For our equation, right, there are possible three different types of quadratic equations that we could use. This was the one that we talked about in our lesson, the vertex form. A equals the direction of the opening. So does it open up or down? The H value tells us the axis of symmetry. So that halfway point or an invisible line that kind of cuts our quadratic in half. And the K value tells us our maximum or our minimum. Together, the H and K give us our vertex or that highest or lowest point. Graphically speaking, we do see a curved line. It tends to be either an N shape if it opens down or a U shape if it opens up. So generally speaking, that's what the models will look like. Now our data may only show half of that depending on what the scenario is, but our models should show a curved line, either a U or an N shape. Lastly, we have our exponential models. Again, looking at a table, we can go through and find the first and second differences. You see that the first differences aren't the same. If we look at the second differences, we can see that they're not the same as well. However, if we check the ratios, let's do that below for sake of space. The ratios when we divide the previous value, so 15 divided by 5 is 3. 45 divided by 15 is 3. 135 divided by 45 is 3. And 405 divided by 135 is 3. So the ratios of an exponential model are all the same. When we look at an equation, y equals ab to the power of x, and a key thing is the x variable is an exponent now. A tells us our initial value, and B tells us our ratio. If B is greater than 1, it's increasing or it's growth. If B is between 0 and 1, it's considered decay or decreasing. graphically, we will see a curved line. It should show more of a drastic increase or decrease than a quadratic. The one thing as well that's different, even though there's a curved line, it either only increases or it only decreases. It's not like a quadratic that has both. So an exponential model is only ever increasing or only decreasing. It's not a combination. Right? So those are the characteristics that set these different models apart. Just kind of a brief overview looking at the tables, the equation, and the graph. Determining the models using Desmos. Again, we had different models that we can enter into Desmos to come up with possible lines or curves of best fit. In each model, we would be given an R value or an R squared value that we can find an R value from, and that tells us how strong of a relationship it is. If you remember the previous unit, when we looked at the line of best fit, looking at the R value, in some cases, if an R value was placed on data that wasn't linear, so it had a low correlation. That's the same thing here. If we can create a linear or quadratic or exponential model, we can create all three models for one set of data. However, there are ones that are better or stronger for the given data set. So even though you can create a model for a set of data, it doesn't necessarily mean that it's the correct one. And that's what we're going to look at next. So we're going to look at a couple of data tables and we're going to enter it into Desmos and see which model is best. So in this case, we're looking at years, every 5 years, and the number of subscribers in the millions. So we're going to go to Desmos. We're going to enter in our table. So click the plus button, select table, and you'd enter in your values. Again, I'm just going to quickly go through it. Now that we have our data entered into our table, we can go through now and we are going to enter in the different equations for the different models. So we'll start off with our linear one, y1 squiggly line mx1 plus b. Oh, we don't see anything, but that's okay. We have to click on the little plus to go to our data. So we can see our data, we can see our line of best fit. It does look like it fits. We can have our R value, our M, and our B value. So we can go through, we can fill that into our notes. So our linear model would be y equals 4.39x plus 120.8. I'm just going to round some values just to make it a little bit easier. The R value, again, we get from Desmos 0.9951, which indicates it's relatively strong, right? It's close to perfect. Let's enter in our quadratic one right after it. So just clicking below into a new box. So y1 squiggly line a x1 minus h bracket squared plus k. So now I have my, if I get rid of the red line, I have my quadratic model. And this one will give me an equation of, again, just getting this straight from Desmos, y equals, the a value is 0.04 times x minus h, or minus a negative 35. So it becomes plus 35.8 squared plus 70.9. So that's our quadratic model. Our R squared, or our R value, we don't get an R value here, so we have to take our R squared and divide it, or square root it. So our R squared value is 0.9974. When we square root that, we get 0.999. So again, almost perfect, even a little bit closer than our linear model. Let's enter in our third one, our exponential, y1 squiggly line ab to the power of x1. Didn't get my power sign there, AB to the power of x1. And we see our exponential model. So looking at it, we get the model or an equation y equals 127.2 times 1.024 to the power of x. The r squared value is 0.99, or the square root of 0.9965, which again 0.998. So looking at these, they're all relatively strong. They're all almost close to perfect. Let me just change this color here. They're all almost perfect. So which one is the best fit? Well, we could kind of reason through some of these, right? So year 0, we have 128.4 million subscribers, and it increases each year. Now, if we look out or we expand to see how it's going to continue, this may give us a better idea. So the blue one, it starts to drastically increase. Have we seen any drastic increases yet? No, not really. We haven't seen anything that's concerning, right? Not as much of a drastic increase, especially over 30 years, that we tend to see. So this is saying that after 40, 50, 60 years, the number of subscribers is going to skyrocket. If you know anything about subscription programs, chances are that doesn't happen, right? Maybe the program ends up dying out, right, or disappearing, or being replaced with something better. The quadratic model, something similar, right? It starts to increase more. If we were to reverse it though, the quadratic model says that we eventually came from a very high value, right? Because year 0, what if we went before? Where were all those subscribers? What were we at? Maybe we were just started taking values at year 0 or at a year that we said was year 0, even though we had data from before. Linear does make sense that we started from a value and slowly started to constantly increase. But again, based on the data we have, either of these could be good. I would argue more for linear because this is over 30 years. So we have a consistent or quite a bit of data in terms of time. I don't see another 30 years or another 5 years doing anything to change it more exponential or quadratic. But again, we don't have those values, right? So based on what we have, we could argue that any of these would make sense. We would need a few more data points or more data in between these values. Or maybe if we had data from every year in those 30 years, that would give us a better sense of how the data is going. But in this case, since we don't, we could argue that any model would work. With our next model, what we're going to do, the nice thing about Desmos is I don't need to get rid of the equation. I just need to change my table. So I'm going to enter in these new values for looking at the maximum price of a season pass and the revenue. So I have my new data entered, and the equations, even though they disappeared when the table disappeared, once you start entering data, they reappear. So now I have my data for these or my models for this table. I think it's pretty clear based on the data which one is the best fit. But let's go through and look at the equations for each of them and look at what R values we get. So linear model, we get y equals m, which is negative 231.9 x, and then plus 64,469. We get R value of negative 0.6992. Quadratic, we have an equation y equals a value is negative 6.1 times x minus 94.1 squared plus 49,492.6. The R value, which is the square root of 0.9973. We had 0.999. In the exponential model, we get y equals 65,240.4 times 0.995 to the power of x. And the R value is the square root of 0.3919, which is 0.626. So looking at these values, again, the R values for the quadratic, which we had guessed right off the bat anyways, just based off of what we're seeing, is the strongest. But the linear and the exponential are still in that moderate, borderline moderate strong window, right? So even though the data may not look like that, we could still have a strong or relatively strong R value. That's why it helps to know the characteristics of these different models. So in this case, I think it's pretty obvious. The quadratic is the best model for this scenario. We have one more scenario. We're going to be looking at the hours since a drug was administered and the amount of drug in the body. So again, we're going to delete our table, or at least the values in the table. And we're just going to re-enter the new values. And with our new values entered, we can see that our models or lines and curves of best fit reappeared with some specific equations. So for linear, our equation would be y equals negative 29.5 x plus 758.9. The R value is negative 0.9044. For the quadratic model, we have y equals 1.54 times x minus 24.6 squared plus 21.9. The R value is the square root of 0.9853, so 0.993. And for our exponential model, y equals 998.4 times 0.89 to the power of x, and we get an R value of 0.9998 if we really wanted to. So looking at these three, again, they're all relatively strong, right? They're all in the nines. One is clearly a little bit stronger than the other, but when you start going down to so many decimal places, does that really matter? Well, I think by looking at the data, I think it's clear that it's not linear, right? It just doesn't form a straight line. It's that kind of drastic decrease. Now, looking at the quadratic and the exponential, the quadratic doesn't go through many of those points. The exponential does, but they both still have strong R values. So you could collect more data, or you could kind of reason through it. If we look at this, we'll look at them individually. What predictions would we make after 30 hours of having the drug administered? Well, based on the quadratic model, it's suggesting that after 30 hours, or even after the 25 hours, the amount of drug in your system would start to increase again. But taking any sort of medicine, is that the case? Does it just miraculously start to increase again? Or does your body absorb it and break it down and use it up? Right? If we know about medicine, we know about any sort of drugs being administered to the body, it wears out, it wears off, right? Your body uses it up, dissolves it, breaks it down, uses it for its intended purpose, whatever the case may be. The amount shouldn't increase again unless you're getting a new dose. But that's not what we're looking at. We're looking at a single dose over a period of time. So the quadratic model doesn't make sense in this case, because why would the amount start to increase again? Right? What's the amount of drug in the body starts to decrease, and over time it almost disappears. It shouldn't start to go back up. So even though we had strong R values, the exponential model fits this one best. One, based on the R value down to the decimal place, and two, based on the given scenario, right? The amount of drug in our body should keep on getting lower and lower and lower, or smaller and smaller and smaller. So in some cases, you may have to reason through it if the R values are all relatively strong. But usually, you should be able to kind of use some common sense or general reasoning for about which model makes sense. You could use how the model would make future values look, or what predictions you'd have to make looking at future values. Right? That's why we know that it's not quadratic, because the amount doesn't increase as time goes on. So the main thing from this lesson is, again, just taking a look at a review of the different types of models, some of their characteristics, as well as learning how to enter them all into Desmos to determine which model best fits a given scenario.